Hello everyone, welcome back to another banger video. Today, we're going to be building an exciting project that involves detecting credit card fraud using machine learning. Credit card fraud is a significant concern in our digital world. Detecting fraudulent transactions is crucial to protect individuals and businesses from financial losses. In this project, we'll leverage machine learning techniques to identify fraudulent activities. Now before we get into the video, if you guys want to see more videos like this, drop a like down below. It helps us out tremendously with the YouTube algorithm. With that out of the way, let's hop right into it. Alright, so the first step is to understand our dataset. We'll load the dataset using the pandas library and take a quick look at its contents. So here we go ahead and import pandas. Let's go ahead and run that. And then a quick way to upload files on Google Colab is to just type in this code right here. You'll be prompted with this choose files button and then just upload the dataset. If you're on the desktop version of Jupyter Notebook, you just have to slide the or drag the dataset into your repository or your directory, and then you can use it right away. The dataset for this project will be in the description. It's on Kaggle. Just go to the description, download it, and upload it. All right, next we're going to go ahead and read our dataset. Right, so here we import the pandas library, which is commonly used for data manipulation and analysis. We load the dataset from a CSV file called creditcard.csv and use the read CSV function. The dataset is stored in a variable called data. By using the head function, we can display the first few rows of the dataset, providing us with an initial glimpse of the data structure. Now let's go ahead and gather some important information about the dataset. Alright, so the shape attribute of the pandas data frame returns the dimensions of the dataset, gives us how many rows and columns we have. By printing this shape, we get an idea of how large our dataset actually is. Additionally, the describe function provides summary statistics for each numerical column in the dataset, including the count, mean, standard deviation, and quartiles. This helps us understand the distribution and range of values in the dataset. Right? To tackle credit card fraud, we need to understand the distribution of fraudulent and valid transactions. Let's now separate them and calculate some useful metrics. Copy that. Alright, let's make sure we didn't make any errors. Looks good. So in this code snippet, we create two subsets from the data set. Fraud, which contains the fraudulent transactions, and valid, which creates the valid transactions. We do this by applying a condition to the class column of the dataset. Transactions with a value of 1 in the class column are considered fraudulent, while those with a value of 0 are considered valid. The outlier fraction variable calculates the ratio of fraudulent cases to valid transactions by dividing the length of the fraud subset by the length of the valid subset. This metric helps us understand the imbalance between fraudulent and valid transactions. Next, we print the outlier fraction, which represents the proportion of fraud cases in the dataset. We also print the number of fraud cases and valid transactions using the len function and the condition on the class column. To gain further insights, let's examine the transaction amounts for the fraud and valid cases. In these code snippets, we display summary statistics for the transaction amounts in fraudulent and valid transactions separately. By using the describe method on the amount column of each subset, we obtain metrics such as count, mean, standard deviation, minimum, and maximum values. This helps us understand the range of distribution of transaction amounts in both categories. Understanding the relationship between different features in the dataset is crucial. Let's visualize the correlation matrix using a heat map. Alright, so here we import the Seaborn and Matplotlib libraries, which are commonly used for data visualization. We calculate the correlation matrix of the dataset using the core function on the data frame. The correlation matrix measures the relationships between pairs of variables in the dataset. Next, we create a figure and axis object using the plt.figure function and specify the size of the figure using fig size 12.9. Then we create a heat map visualization of the correlation matrix using SNS heat map. The Vmax parameter sets the maximum value of the color map, while the square parameter ensures that the heat map has square cells. Finally, we display the heat map using plt.show. So here's the heat map. It provides a visual representation of the correlation between different columns in the dataset. Darker colors indicate stronger positive or negative correlations, while the lighter colors indicate weaker or no correlation. Alright, so now that we've analyzed our data, it's time to prepare it for training our machine learning model. We'll split the dataset into input features and the target variable, and further divide it into training and testing sets. Alright, so in this section, we import the train test split function from the scikit-learn library. This function allows us to split the data into training and testing sets for our machine learning model. We assign the input features to the variable x by dropping the class column from the data frame using the drop class axis1 right over here. The target variable class is then just assigned to y. To process the data in the scikit-learn model, we convert x and y data frames into NumPy arrays using the dot values attribute. The process input features are stored in the x data variable, while the target variable values are stored in the y data variable. Finally, we use the train test split to split the data into training and testing sets. The x data and y data arrays are passed as inputs, and the test size parameter is set to 0.2 to allocate 20% of the data for testing. The random state parameter ensures the reproducibility by fixing the random seed to 42. Alright, so now it's time to actually build our machine learning model. We'll employ a random forest classifier, which is known for its effectiveness in classification tasks. Alright, so here we import the Random Forest Classifier from the scikit-learn library, which represents the random forest model. We create an instance of the Random Forest Classifier called RFC. Next, we train the model by calling the fit method on RFC and passing the training data xtrain and ytrain. The model learns from the input features and their corresponding values. Once the model is trained, we make predictions on the test set xtest using the predict method, and then we store the predicted values in the ypred variable. Alright, so this is going to take a while to train just because of how big our data set is. So we're just going to move on to trying, we're just going to write the code that's going to next assess the performance of our random forest classifier. We use various metrics like accuracy, precision, recall, F1, and the Matthews correlation coefficient. Now I'm just writing these out for now, but we're going to need the entire model to be trained before we can actually test how it did. Alright, so in this code snippet, we imported several metrics from functions from scikit-learn, such as the accuracy score, precision score, recall score, F1 score, and Matthews correlation coefficient. Now, by comparing the predicted values with the actual values of the test set, we can calculate the accuracy, precision, recall, F1 score, and Matthews correlation coefficient. These metrics help us evaluate how well our model performs in detecting fraudulent transactions. And now I'll be back once this model is trained because it is going to take a while. Alright, so now that our model is trained, it took 6 minutes, we could go ahead and run this next code block to get our accuracy. And finally, what we're going to want to do is visualize the performance of our model. So we could see that the accuracy was pretty high, the F1 score and the recall were a little bit lower, but overall it seems to be pretty accurate in detecting fraud. So now let's go ahead and visualize the performance of our model using a confusion matrix. Let's make sure this is accurate. There we go. Right. So here we import the confusion matrix function from scikit-learn. This function allows us to compute a confusion matrix which displays the true positive, true negative, false positive, and false negative predictions made by our model. We create a list of labels to represent the classes, which are normal and fraud, and then we call confusion matrix to pass the true labels ytest and predicted label ypred as the inputs. The resulting confusion matrix is stored in the conf matrix variable. To visualize the confusion matrix, we create a figure using plt figure fig size 1212 to specify the size. Then we use sns.heatmap to create a heat map of the confusion matrix. The x-tick labels and the y-tick labels, anot, and fmt parameters are used to customize the heat map's appearance and annotations. Finally, we add a title to the heat map using the plt.title functions, set labels for the y and x axes using the plty label function and the pltx label function respectively, and we lastly display the plot using the plt show. Alright, so that concludes our coding tutorial. We've explored this code step by step and explained each line and its purpose. If you guys found this helpful, or if you guys want to see more, drop a like, subscribe, and we'll catch you in the next one.